Okay, now that we've compassed a shock tube, right, we started learning the flow property changes across an expansion fan. We started with learning, doing a brief review of how things work in terms of wave propagation, right. And we used linearized equations. We introduced the concept of how we could use small perturbations, right. The way property changes in when there is a wave disturbance or a wave is traveling is considered to be a small disturbance over the ambient. So that's something we sort of dealt with at the time. So let us just sort of look at a problem and see if we can use that concept here, right, and solve equations and get some information about the flow properties. Okay, so say we have a problem like this. So let me draw this. Okay, so let's just say okay, I need to draw a straight line here. Okay, that's as straight as I can go. Fine, so we have the x-axis like that. Okay, so I'm going to draw this okay. Okay, so what we have here is this essentially this is called this wavy wall problem. Okay, so okay, this is the wavy wall problem. So in this here, so essentially what this is, let's call this as L, which is the wavelength. Okay, this could be lambda if you want to choose it that way. Okay, this is the amplitude, of course. This is the amplitude. H. Okay, and the y ordinate is given as YW or Y wall, right, and this is actually given to us as okay. So this is essentially the problem. So what we need to do here, is assume that H is small. So essentially considering this as a small perturbation problem, find out an expression for the velocity potential, which is phi, right, and the surface pressure coefficient, the pressure coefficient at the wall. So this is what we need to find out. Okay, so what I'll do here is just write out the velocity potential equation just to sort of remind you. Okay, so okay, before I do that, so essentially what is happening here is that we have a flow, right, we have a flow which comes in like that, right. So incoming free stream is at a Mach number which is m infinity, right. And then we are going to do this problem to find out velocity potential phi and coefficient of pressure at the wall. Okay. Now, for irrotational flow, right, for irrotational flow, we know that the velocity can be written in terms of the gradient of the velocity potential, right. So, that is essentially for an irrotational flow, and let me just write out the velocity potential equation just to remind you, okay. And that is okay. So, this is essentially the velocity potential equation. Okay. So, now let us just basically the point is that when you have a free stream, so we have a free stream and then suddenly it encounters this wall, okay, which is a wavy wall like this. So, how does the velocity in that flow field change, which was just a free stream, and it encounters a wall like this. And in this particular case, so the nature of the wall or the contour of the wall is given, right, which is by this expression here, right. And so, we need to basically assume that this is a small perturbation. So, what would that mean in terms of linearizing the equations that we will use? So, this is our problem. So, okay, so let us go ahead and try to solve this. So, let us write our free stream. So, our free stream is essentially in vector form. This is how it is, right. This is my free stream, and say the local velocity. So, then the local velocity right. So, local velocity, we are going to call that this, is equal to this is the total local velocity. Okay. So, then let us say that the perturbations in the velocities are so. So, the perturbation velocity, you can call that okay. Say let us call this as q, is say we are going to call that u prime okay. So, essentially we have a free stream, right, we have a free stream which has, and we have a perturbation velocity which looks like this, and we have a local velocity of this. What is the connection between these? If we consider perturbation theory as we talked about earlier. So, the free stream is perturbed by this velocity to get the current local velocity, right. So, if we do that, okay, so if we essentially do that, which means that what we have here in here is that this V is nothing but the isn't it. So, this is my local velocity, which is the free stream plus the perturbation, right, which means that what we have here is this. What we have is u plus okay. So, essentially let us say, okay, right. So, this is the, so therefore, this is the local velocity, which means where essentially this is my u, this is my v, this is my w, which is the local velocity. So, I have the free stream which is perturbed using this perturbation velocity, we get the total local velocity. Okay. So, now as you can see that for the, if you have a velocity potential like this, you can represent your local velocity in terms of gradients of that potential. So, similarly, we can have a perturbation potential corresponding to this velocity. So, let us say that we have a perturbation potential which is, say this is corresponding to a perturbation potential phi p, and this is corresponding to a perturbation potential, sorry, this is corresponding to a potential phi. So, which would mean, right, which would mean if you sort of look at this equation over here. So, essentially, so this is the local velocity which is equal to the perturbation velocities, right, plus the free stream, isn't it? This is what we get. So, this is my local velocity which is corresponding to this perturbation potential, corresponding to this potential, okay, that is equal to the perturbed velocities which is given by the gradient of a perturbation potential, and this perturbation is applied to the free stream, right. So, therefore, this is what we get. So, hence from here we can write, if we integrate this now. So, therefore, say phi is equal to phi p So, essentially we need to find out a potential for our wavy wall problem over here. We need to find out the potential, so that once we find the potential, we shall know the flow properties, the velocities as well, right. So, now what we see over here is that the surface potential for the wavy wall can be written as a the component of the free stream plus a perturbation potential. So, as long as we can find the perturbation potential, we should be now be able to find the surface potential for this kind of problem. Okay, so, now we have this. Okay, so, let us say call this as, okay, so let us say, let us call this equation out here as 1. Okay, and we shall call, say, this equation as 2. So, we can now write, so therefore, you see this is the velocity potential, and correspondingly this is the velocity potential equation, right. Now, we said that using a perturbation theory, we are able to write this potential as a free stream potential plus a perturbation potential, which is what we derived here in this particular equation. So, now what we will do is we will use this equation into one and see what we get. Okay. So, this is going to be, well, it is almost like a half page equation, but I will write it out, okay, just to sort of scare you, okay, and then we will see what we will do with this. Okay. It is important to write this. So, okay, so if I were to write this, so essentially I am using the surface potential equation that we got here into the velocity potential equation. Okay. So, it looks like this. Okay, this is the left hand side, right. So, what we get here is on the right hand side, okay. Okay, this is going to take me a while to even write this. So, okay, so we have got the second term here, which will be okay. Well, there is of course a certain, okay, okay, okay. Okay. Okay, then okay. Okay. So, hopefully you are all awake by this time. So, this is what it looks like. Okay. If I incorporate the perturbation potential, right, into the surface potential equation, then the velocity potential equation looks like this. Okay. So, this is an exact equation, as you can see over here, it is an exact equation, and although the left hand side out here, which is this, is linear, clearly the right hand side is not. Okay, you can see this. So therefore, what we are going to do over here is bring in the small perturbation theory. Okay, so if I do that, small perturbation theory essentially will mean right. So this, and hence their squares and higher orders will be negligible. So this is my small perturbation, this is my small perturbation assumption. So if I use the small perturbation assumption here, then what I should be able to do over here, as you can see, if you look at each term over here, so all these terms here, so say let us look at this. Okay, so we have u dash by v infinity, the square of that term, and we have squares, etc., etc., etc. So now all of these terms, so these terms can be neglected, right, because we are using small perturbation theory, and if we do that, what we see is that essentially what we are left out with this equation. So if I call this equation as say 3, okay, if I leave this out, all I get from there is right. So this is what we get, and let's call this equation as 4. This is what we get, and of course we can also, so we basically have written our velocity potential equation in terms of this. You can see this now reduces, if I use the small perturbation theory, this is our velocity potential equation essentially is in terms of the perturbed velocities, right. So I can also write this, as in terms of the perturbation potential, right, perturbation potential, which would be right, and let me call this as 5. So what you basically see over here is that these two equations here, 4 and 5, right, which we get by using the small perturbation assumption into the exact nonlinear equation, surface potential equation in 3. So unlike 3, these two are linear equations using the small perturbation theory, right. And in here, so now we are going to use, say, so basically we have an expression in terms of this. Now if, so now basically we will go ahead and try and solve this. Now for this particular case, again let us take the 2D version of this, which would be essentially this equal to 0. So if I take that, how do I go ahead and solve this? Okay, so let us go ahead and do that. Right. So essentially what we have in 2D, okay, this is what we have. Okay. So, this is this is the governing equation now. So, how do we go ahead and solve this? Now, what we will use here is a method of the separation of variables. Okay. So, this is the mathematics part of it. So, this is the part of calculus. If you are not if you don't remember it, I think you should just go and run yourself through it, one should be fine. I will walk you through the whole procedure of this, okay, but I will not go into details of the mathematical derivations and all of that. Okay, but we'll walk step by step through the process of it. Okay, so using the method of separation of variables, so the way we will basically write is say right. So, f and g are just functions, okay, as so f is a function of x and g is a function of y. So, this is separation of variables. If I do that, right. So, if I do this essentially, so if you see here, so essentially what we get is this, isn't it, right, and therefore okay. So, similarly if you look at this, okay, del v, so this is okay. So, this is what we get from here. Now, if I do this, so let us now use okay, so let us say, so this is say our equation A. So, we have this expression here and this expression here using a separation of variables. So, if I do this, so therefore, I will use B and C into A. So, if I do that, what do I get? So, if I do that, what essentially I get is, right. So, del to phi del x2, so that is del to phi del to phi del x2, okay. So, which is okay, plus del to phi del del y2, which is this thing. Okay. So, again now what we can do is divide this whole thing by f g. If I divide this whole thing, so if I divide by f g, okay. So, okay. So, this is the relationship that we get, and finally, what we will do is we will divide this whole thing. Again, we will take okay. So, finally, we can also write this as okay. We will just take this term, divide by this term throughout. So, again what we will get is okay, and let us call this as say t. Okay. Now, this is it. Now, let us say that x is held constant. Okay. X is held constant. So, f is, or say x is held constant, and so y varies. So, we will hold, say, x is constant, right, and y varies, right. So, which means that okay. So, this is a constant, say, and let us call this as okay. So, this is a constant. Okay. So, which means that so again, so if that is true, so therefore, from D what we get is that 1 by right, and this is constant, right. So, we are saying that we are going to hold x constant and y will vary, and so what we see from D is that this term is, we just take this on the right hand side, which is this is a constant, and let us call this as, we just call this as omega square, you know, just say it is, say, omega square. Now, if I do that, then from here, so basically we get two relationships, don't we? So, for example, if you look at one of this, so essentially what we get is that this is equal to a constant and this is also equal to a constant. So, we get two relations from this. So, which are, if you just sort of look at this, from this what we get is okay. Okay. So, this is one relationship and let us call that as, say, E, and the other one we get from here, which is okay. So, essentially these are my two relationships. Okay. So, using the separation of variables, f and g being arbitrary functions, and what we get from here is these relationships where this f and g are arbitrary functions and omega here is a constant. Okay. So, now if we can find appropriate values of f, g and omega, then we should be able to sort of solve this equation. Now, the reason we write this equations in this term, we wrote this in this form because this has a ready-made solution from us. This is from our calculus, right. So, we have a ready-made solution for this, which will be okay. So, the solution to these equations, say E and F, is given in this form. So, then G solution is given as, again we have constants okay, and f(x) has okay. So, this is my ready-made solution. So, if we can find appropriate values of a1, a2, b1 and b2, then we should be able to find out fx and gy, and hence we will be able to find a solution for our velocity, perturbed velocity potential, because phi p is equal to fx into gy. Okay. So, let us see if we can do that. So, usually how we go about this is that we try to see if we have enough boundary conditions, right. Then we can see, so if we can find appropriate values for this. Okay. Now, you see of course, phi p. So, even if we have, so phi p is a finite value, right, which is the velocity, the perturbed velocity potential. Perturbed velocity potential out here has a finite value for all cases of x and y. So, we have nothing here to tell us that the velocity potential blows up or becomes indeterminate or discontinuous. So, therefore, even when y tends to infinity, right, we have a finite perturbed velocity potential. Now, let us look here. Now, when y tends to infinity, okay, now when y tends to infinity, look at gy. Okay. Now, this term becomes nearly 1, right. So, because this term becomes to the negative infinity. So, this term, this exponential over here will tend to nearly 1, whereas what happens to this term here, this tends to infinity as well, right. So, therefore, if to keep this as really finite, right. So, in this case this means that we have to set a2 equal to 0, because otherwise right. So, therefore, when y tends to infinity, what we see over here is that if y tends to infinity, gy will tend to infinity if we have a2. This first term out here, so this exponential will tend to nearly 1, but this exponential out here will tend to infinity. So, therefore, unless and until we have a2 0, we will not have a finite value for g. So, therefore, if y tends to infinity, then a2 out here should be 0 to keep it finite. Okay. All right. So, now the next thing is, so we have a wall here, right. We have a wall given over here, and the equation of the wall is also given to us. Okay. Now, we have this flow moving over the wavy wall. So, definitely, so when the wall, say, so if I take a streamline which is, say, on the wall itself, how will the streamline look like? So, let me draw some streamline vectors, right. So, this will be my local velocity vector, then this will look like my local velocity vector. So on and so forth. So, essentially what I am doing over here, I am just saying that my velocity vector is tangent at the wall, the velocity vector is tangent to the wall, right. So, therefore, the flow is tangent to it, right. So, therefore, another boundary condition is flow is tangent to it, right. So, therefore, now in here if we sort of go back over here. So, this is my say let us look at, for example, this velocity vector over here, okay, or say let us look at this velocity vector over here. Now, okay, so this was the original streamline, right. How do we get this local velocity? So, we get it with a free stream which has been perturbed by u prime, and this is the v prime in the vertical direction, right. So, this is essentially my this is essentially how the velocity profile looks like. Okay. So, this is the local velocity. So, if I may sort of highlight this a little more. So, this is my local velocity vector, right, and if I see the components of it, the horizontal component, the x component is the free stream plus the perturbed velocity, x velocity, and in the y direction is the perturbed y component of the velocity. So, therefore, if I have to take the tangent, right. So, what does the tangent mean over here? So, at this point, okay, at this point, therefore, at the wall, can I write it as this? Right. So, this becomes the tangent. So, therefore, that is what I am going to do over here. So, tangent to it. So, essentially what I am saying is that dy by dx, right, at the wall, okay, is well, I use a subscript w for wall. So, essentially this is the wall velocities here. Okay. So, if I do that, now what we will do here is essentially consider small perturbations, right. If we consider small perturbations, what we know here is that that u wall, u prime, right. So, which would mean that I can actually write this as, right, I can actually write it like this, right. If I can write it like this, then this I can also write in terms of the velocity potential, perturbed velocity potential, which will be right. So, therefore, slope, okay, the slope out here is the Vw prime this, and then I write Vw in terms of the perturbation potential, okay, gradient of the perturbation potential in the y direction at the wall. So, this is an expression that we get. Okay. Now, if I do that, let us so therefore call this expression as, label it as 1. Now, so this is from the velocity component, the velocity consideration. Now, the wall, the contour of the wall by geometry in terms of x and y is also given to us, right. Since that is given to us, we can also do this. Right, since that is given to us, so which is right. So, therefore, if I consider the slope of the wall, right, what I get is right. So, this is what we get, and let us call it this as 2. Okay. So, this is from the geometry consideration of the physical wall itself and from the velocity considerations. So, let me write that again. So, from the velocity considerations, again what we got is that the slope is this, right, and this was 1. So, clearly this is from the velocity consideration and this is from the geometry consideration. So, let us put these two together, right. So, basically therefore, if this is equal to this, right. So, if if this is equal to this, so therefore, what we get from here is that del phi p del y, right, at the wall is equal to minus 2 pi h by L into V infinity sine. Okay, so we have okay, and let us call this as say G. Okay. Now, if I do this, and of course, we have reduced our A2 has basically gone to so A2 has basically now gone to 0. So, del phi p, so we have this expression, right. So, now the next thing is that essentially having done this, so now we know that phi p is f x and g y. So, how do we write this? So, now f x is essentially okay. Okay. Now, G y if you look at this, we said A2 is equal to 0. So, therefore, we are left with this. Okay. So, which is A1 exponential right. So, we have this. So, now what we will do here, is that we will take, we will find out del phi p del y. Is that? If I do that from here, what I get is this doesn't change. So, if I do this, what I get is A1 into okay, into y. Okay. Now, what we will do is, now we need basically at the wall, right. Now, at the wall, now let us come back here. So, essentially we need the del phi p del y at this wall. Okay. Now, we have assumed small perturbation, which means that h is very small, which means that, so if I use a small perturbation theory, so then we say that h is very small, which means that this wall is very close to y is equal to 0. So, if I take here, so del phi p del y at the wall would also essentially mean that we are saying del phi p del y for the y direction to be almost 0. Okay. So, if I do that, what do I get here? What I get from here is minus A1 into this okay, I think I missed out into okay, into this. Okay. So, let us call this as, relationship as, I. So, essentially now what we have done is, now we have a del phi del y relationship, okay, which we derived considering the physical slope which was given to us and the velocity considerations here, and we got an expression for that in terms of x, right, x here and this expression. Now from here, now then again this is from our math that we did. Okay. So using this relationship, that our velocity potential which we are using over here is essentially written in terms of this f and g. We input that in here, okay, and then we wrote an expression for del phi del y. Now we need the del, we have an expression, a specific expression for del phi del y at the wall. So using a small perturbation theory, we said that this del phi del y at the wall for a small perturbation, which means h is nearly 0, which would mean that it is nearly 0 to the y ordinate being 0, and we get this expression. So next step is of course to equate these two. Okay. So we will continue with this in the next lecture. Okay. Thank you.